Hello everyone, it's December 28th. All right, let's get to it. Oh, we have another hard one. All right, let's take a look. All right, again, something we've done before. Have I added this to? Okay, it's not in the 9 minutes, so probably it's not that hard. You want to schedule a list of jobs in D days. Jobs are dependent. To work on the ith job, you have to finish all the jobs j. Okay? You have to finish at least one task every day. The difficulty of a job schedule is the sum of difficulties of each day of the D days. Wait, what the hell is D? D is the number of days. The difficulty of a day is the maximum difficulty of a job done on that day. You are given an integer, a job difficulty, and an integer D. The difficulty of the ith job is difficulty I. Return the minimum difficulty of a job schedule. If you cannot find a schedule for the job, return -1. Okay, what the hell is the schedule? Jobs are dependent. To work on the ith job, you have to work on all the previous job. That is the schedule, right? You have to finish at least one task every day. The job difficulty is the sum. The difficulty of a job schedule is the sum of difficulty of each day of the D days, okay? And the difficulty of a day is the maximum difficulty of the job done on that day. All right, let's take a look at the example. Job difficulty is this. D is equal to 2. First day, you can finish the first 5 jobs. Well, you have to go job from 0. So the first job you have to do is job 0, right? And the second job is, and since you're already done the most difficult one, you might as well just do all of them. And you cannot do all of them because the second day you have to do at least one. Yeah, that makes sense. First day you finish the first 5 jobs, total difficulty is 6 because it's the maximum. And the second day you finish the last job, okay? The second example, D is equal to 4. So you cannot find a way to schedule 3 jobs in 4 days because one of the day will have no job. Okay, so that's -1. Example 3, the schedule is 1 job per day. The total difficulty is 3. All right. All right. What do you think? I have no idea. That's some DP for sure, but I just need to figure out. Okay, just come on, get your IQ up and try to figure out what type of DP can we do. Okay, so we have days, right? So we have the first day, second day, and the third day. And it is required that to get the ith job, you have to do all the previous job, which means for the first day, this is the second day, third, we might have more days, which means in the first, we have to do job 0, right? We have to do job 0 because you cannot do job 1 before doing job 0, which means it's going to be, we can rewrite this problem as a list. So we have job difficulty, right? So job difficulty, we can call it D0, D1, D2, to Dn. We have n jobs. I might do n-1. And for each day, we have to finish. So first they have to finish at 0, right? We cannot do 2 before finish 1. So basically, we're saying, given a list of numbers, we want to partition them into subarrays, right? So the question is, after we partition into subarrays, and we have to partition into, so yeah, given an array of numbers, right? Partition into D subarrays, right? Partition into D. I should not use D, just get confused. Let's call it J. J. Right? We're partitioning into D subarrays, and the value, right? We can call the score. The value of each subarray is the max of J's in the subarray, and we want to find the min, right, of the sum of all subarrays, subarray values. This is what we want, right? This is what we want. So we convert the problem into this. And of course, if the length of job difficulty is smaller than D, the answer is no, is nothing. If it's equal to D, the answer is just add them up. So these two are like trivial cases. So it's kind of it's a max min kind of problem. So usually you would think maybe can we do, can we do, like, let's say a binary search, right? Can we do a binary search on this? We can try. So binary search, basically we have the minimum score, which is just basically 0, right? And we have the maximum score, which just add everybody up. And we can create some, and then we have, say, okay, can we reach the current score, right? Can we reach the current score? So can we figure out some way to go through to see if it's possible to reach that score? Now, how do we do that? Because we have D, so we have to split it into, so we have to put, we can do O(n) squared log n. That is allowed because it's only 300, so we can do O(n) squared, which means, can we split it into, so we can go from the front, and then we can go, basically we keep track of the max value, right? And then we get the max. The max will always be, the max value will always be kept, right? Yeah. But yeah, it's a the first subarray, we have the max value, right? The second subarray, we have the max value. The third subarray, we have the max value. But there are many ways to do it. So I don't think binary search will be the way. Let's go back to DP. Okay, let's go back to DP. So we can say, usually this, yeah, we can say, let's see if DP index and the remaining, it's just the same. It's the same way as kind of yesterday, right? So DP index and the remaining, we say we'll find the minimum, okay? Minimum values for job difficulty from I index towards the end with remaining number of subarrays to do, right? Let's say this is what we trying to do. Okay, so how are you gonna do? So we have, an array, again, J0, J1, J2, all the way to J(n minus 1. And I say current, this is our index, okay? Now we have index towards the end. We have this. We want to find, and then we can divide it into remaining number of subarrays. And then what? We'll go from here, one by one, right? Kind of give you a hint because the length is so slow, so small, so you can go one by one. I can say, isn't this exactly the same as yesterday's? And we use exactly the same idea, right? Because, all right, so, okay, I think I know how to solve this. We go from back to the front. So at the end, when we find the answer, right? The answer will always be a chunk, right? The first subarray, the second subarray, third subarray, whatever. So whenever we have the index, if the index is, right, the start of some subarray, then if we go one by one, we will always end up at something. We don't know what that something is, right? We always end up at something, which this subarray is the answer. And then we just need to find the remainder. So that's exactly the same. That's exactly the same. So do you want to entertain the idea of using Java because it's the same as yesterday, which means the difficulty of implementation is not as high as yesterday. So let's Java this. Yeah, let's Java this. Of course, for Java this, the first thing we need to do is, it's index, right? And it's D, which means we can do an int memo new. Oh, let's not do this. Okay, and we can say int int m int n. Okay, so int m, which one? Int m equal to d. Int n is equal to job difficulty dot length, and memo. That's not right. That's not right. I already handled it. And memo shall equal to new, come on, int m n. Okay. Right. And we'll create a function called private int dp, which will take an index and will take a remaining. Okay, so we can say if because we want to find the minimum, right? We want to find the minimum. But anyway, the first is, oh, hold a second. We cannot use int. Dude, we have to use integer. Because we need to check if something has been, yeah, we say if memo, no. If it's not enough, right? So if n minus index, that is the total job remaining, right? Total job remaining is n minus index. If the total job remaining is smaller than remaining, right? Then we shall return, it's not possible, integer dot maximum, max value. Pretty fun, right? It might overflow though. That's the thing. That is the thing. It might overflow. So to be on the safe side, I want a max value, because I have been bitten by this stupid thing many times. So max value will be, I think, 300 times 1000, and we do 1. Right, that's the absolute max value. So we just do a max. We'll return a max, right? And we say if n minus index, is equal to, so we can add them together. Yeah, okay, I can do that. And we'll return I think it'll be fine. We can do this. If memo index and rem is not equal to null, right? And we just return memo index and remaining. Done. Otherwise, we'll set memo index remaining equal to max. Okay. Then for int I equal to index I smaller than n I plus plus. Right, we go through every one of them. And what if rem is equal to 0? So if this is smaller than rem, or remaining is smaller, and also we have to make sure, yeah, so remaining, okay, so if remaining is smaller than 0, okay, or how do we say this? We still have remaining, but we don't have enough, right? That handles that already. Yes, so the first case, right? This case is when we don't have enough subarrays, and we have another case is we run out of subarrays, right? We run out of subarrays, so both is impossible case, so we handle that. And the other case is for here, right? So we go from this all the way to the end, and we need a max, right? Int max shall equal to 0. Okay, and we say max is equal to math.max and that's actually should get to -1. Max and job difficulty. Oh Lord. Int job diff, and we can say job diff is equal to job difficulty. I just don't want to pass job difficulty anymore. So job diff I. Okay. So this will keep track of the maximum, and we'll say memo index rem shall equal to math.minimum memo index rem, and the current max plus dp I plus 1, right? And the remaining -1. There we go. Yeah, so we go through every single one, we get a current range, and then we have the remaining. Get a current range, have the remaining, current range, and remaining, until we hit a point where we cannot go on anymore, which actually we can handle it here. So I don't go all the way, right? So we go until n minus I is still a larger equal to remaining, right? So we avoid, so once it gets too much, right, you don't have to. So when I gets bigger at a certain point, we will end early, which is perfect, good. And once we're done, we'll return memo index and rem. Okay, so that's our private function. And at the end, we just going to return, because what we want is dp start from 0 with d, right? Start from 0 with d. I can yeah, I just realized I don't need to use intemp, so I'm gonna remove a few. So I don't think I need these. Okay, really don't need this. And this we can just by calling it job div.length, which is perfectly fine. Job div.length, right? It's fine. I don't need to do anything here. And we don't need this. We don't need this. So M is roles. That's actually I got it wrong. Oh, because I do index and the remaining, but it's fine. Job difficulty.length, and this is D. So it's a very thin, right? Very thin. And now we have this, and eventually we do this. Okay. Let's check. See if it works. Oh, it does not work. For 1, it's out of range because I need to do, my bad, this is d plus 1. So for 1, this is d plus 1. For 2, we need to have a int res equal to, right? Then we shall return res is smaller than max, right? Then we return res, otherwise return -1. Okay, 23. All right, let's try one more time. That is interesting. I think I know. So this and I is smaller than job div.length, right? I need to be smaller than job. But if I become big, I don't know. I feel like that's not really the reason. Index 6 out of bounds of length 6. That's the first one. Index 6. Oh, yeah, because this can be. Oh, yeah. Okay, that's fine. So we'll do this, smaller than, and I need to be smaller than job div.length. That's totally fine. Just add more conditions there. You gotta be kidding me. It's true. So this is fine, and then it should be if index is equal to job div.length. Or index is equal to job div.length. And wait, what's this? Because index is getting bigger, right? And if it's smaller than, so basically job is equal to, if these are two are equal, and we don't go through the first one, because in the first one, like if index is equal to job difficult length, then this will be 0, right? Then rem is larger than 0. or rem is more, so rem must be 0. So I do this one is sufficient. That should return 0. Yeah. Come on. That is right. So there are two conditions, right? There are two conditions. All right, let's go for it. Yeah. Yeah, it was not bad. It was actually pretty bad. Come on. Who said it's not bad? It was pretty bad. It's 7%. Come on. But we did solve it. And I'm pretty sure if we can be simplified, right? It definitely can be simplified if you want to do bottom up. If you bottom up, you probably can see where the simplification is, but top down, nah, I'm not quite sure. It's probably, I don't know. I kind of don't want to do bottom up, but let's just finish this one first. Okay. So this problem is, I won't say identical, but it's very, very, very similar, right? Very, very similar as yesterday. This problem is very similar to yesterday's. What is yesterday's problem? What is the, hold on, I can figure out. Yesterday is 2023, 12, challenge, 28. Oh. No. 28. Yesterday was 1531. Okay, 1531. But first of all, we need to rephrase the problem as such. Given an array of numbers, divide it into d subarrays such that the sum of the max value of each subarray is minimized. What is this minimum value, minimum sum, right? That is kind of rephrase the problem, and we use dp index remaining as the recursive function to compute the min sum of the array from index to the end with remaining number of subarrays. Subarrays allowed for and we go within the recursive function. We go from I equal to index to the end, and basically and create all possible subarrays starting from index ending at I. Right, we find the max in it and call dpi plus 1 and then minus 1, right, to get the minimum of the remaining. Yeah, this is the part that resembles 1531 the most. At the end of the day, we have mn, well, we can call d ond, where n is equal to length of job difficulty. but we have a very, very poor performance. Okay, so now the question is, how do we review this? Should be 29. How do we figure out a faster way of doing this? It's probably bottom up, but we need to think, right, how we can do bottom up. Wow, this problem. Oh yeah, stuck a long time. Bottom up. I don't know. Usually top down shall be able to. Oh, that's actually not OMN. That's ON squared. Dude, that's ON squared. That's ON squared D. Because we have to go through N, right? And outside is, yeah, it's ON squared D. So maybe we should get it down to ON. How? Well, if you look at this, right, we basically need to find the minimum value. Yeah, we need to find the minimum value. All right, if we can do bottom up, we will be able to figure out. Do you want to try bottom up? I do want to try bottom up. So bottom up, we have to think completely in the a different direction. Let me see. Bottom up, basically, we say we have something ready already. Like so, bottom up will be J0, J1, J2, all the way to Jn minus 1. So bottom up is we have figured it out. So it will be dp. We can call. Is it remaining? The number of subarrays, right? So I actually am going to change it. So it's going to be a number of subarrays. And already, so we call it DPS sub. So number of subarrays and index. Okay, so this tell me the minimum value of the up until index and divide it into however many subarrays. So now we're looking at index plus 1. In this case, let's just call it dpij then. Okay, we call it dpij. Okay, so we know all the way to dpij. Right, we know dpij, and we are doing j plus 1. Right, so we have j plus 1 here. So what we do is from j plus 1, we're walking backwards. Okay, we're walking backwards, and for each I, yes, for each I, we're walking backwards. For each I, we're walking backwards. For each I, we're walking backwards. And we do the same thing. We're walking backwards to find, to find something. Right, we're walking backwards, so we have a new subarray, right, ending at this. We have a new subarray ending at this. We can get its max. Then we want to know. But this is like a new subarray, right? So we create this new subarray. So how many subarrays do we have in the previous? It's a good question. How many subarrays? Maybe we should start from the last value. So basically we need 3 subarrays. Hold on. We can have 1 subarray, right? Okay. So once we have 1 subarray, we need to have 2 subarrays. So 1 subarray, not really a subarray. We have a prefix max. Okay. Imagine we have a prefix max, right? We have a prefix max from J0 all the way to this. And then that's kind of like 1 subarray. And then we say the second, if we want 2 subarrays, right? Then we starting from this one. We have whatever the J value. And we know the previous max, right? We know the previous max. This one will be the previous max. And then we use this plus this, right? And then that will be 2 subarray up ending here. So we have a value. And then we keep moving this way. So we have a value. We keep moving this way. We have a value. So we have the value of the 2 subarrays. The start of the second subarray. How do we oh, hold on, it's right on my lip. I feel like I'm getting very close. Yes, I can get 2 subarray situation done. How about 3 subarrays? 3 subarrays, I need this, and then in this range, right, in the previous range, if 2 subarrays, what is the minimum? We don't know that, right? We don't know that. All we know is should be up until here, right? Up until a certain position, what is, so up until this position, what is the minimum? I have to go through the whole thing. And then up until this position, what is the minimum? We have to go through the whole thing, right? So now I know up until every position, what is the minimum for 2 subarrays. So in this case, it's still O(n) squared times d. I don't see any reduction in time unless the process of looking can be faster. But how can the process of looking be faster? So we still have to go through the whole thing, right? Because this is always the max. I mean, I can have a prefix max. Okay. And a prefix and suffix max, right? Then we just go through the whole thing. Suffix max and prefix max. It's not really prefix max. Yes, yeah, the prefix max. Now, shouldn't that be the prefix min? No. It is if we have 2 subarrays, right? So we have 2 subarrays. We need to find the minimum, and then you have the max. So that's the prefix min, and then the suffix max. So you do still have to go through every single time, right? You go through every single time, and each time you go through this, you have a prefix min, and then you just go through this once. And you go from right to left, then you find But no, I don't know. Like, what will be the best way? Okay, let's check our previous effort. 34, 34. This is definitely fast. Yeah, OND. This is OND. Oh, a stack. Yeah, I know this OND can do. All right, let's read. I couldn't figure out how OND. Stack to reduce the amount. We use DP and the temp. The previous and current DP state. DPI is the minimum difficulty from 0 to I for the jth plus minus 1th day. Temp is the minimum scale difficulty for the jth day. Okay, so DPI is the minimum schedule for the j minus 1th day. For the j minus 1th day, which is the j minus 1 subarrays. Okay, j minus 1 subarray. So when we are at temp I, which is for the j minus 1th subarray. So it's okay. So basically we're saying we are dividing it into, let's say, 3 subarrays. And then we're at temp I. And when we are at temp I, we first look back at dpi minus 1. Okay, so dpi minus 1 is, yes, the temp I equal to dpi minus 1 plus, that is correct, right? But then you have to go back. That's where the problem, right? Then we consider whether it is possible to group job I with any of the previous jobs. For each day we maintain monotonic. For each day we maintain a monotonic decreasing stack which stores the indices of the job with decreasing difficulty. We compare job difficulty I with the tail of the stack. If the tail is smaller, then we have the possibility to group all the jobs from job stack to job I because they will all have the same max difficulty. That is correct, which is job difficulty I. This might reduce the counting of multiple local high job. Once we reach job stack I that is larger than job difficulty I, we have the possibility to include job difficulty I into job stack minus 1. Once both conditions are considered, we'll have arrived at the minimum difficulty for the current. Ooh, hold a second. What are we talking about? We're talking about a monotonic decreasing on the previous jobs. A monotonic decreasing on the previous jobs. And we are pushing the indices into it, okay? And for the current job coming out, I need to go towards the left, right? But we don't go through them one by one. We will check the top of the stack. If it's smaller, then we can eat it because it's not going to make any difference. So we just keep going through until we hit something that's bigger. Yeah, because okay, I need to check. I need to see. I in range. So for k in range D, yes. So k in range D. So that's true for I in range k to n. Temp I equal to dpi minus 1 plus if I larger than 0. That's true. So we have the first difficulty. While stack and job difficulty I is larger equal to the tail, and then we just pop. Yes, so we pop because they do not change. So basically this is saying for the current day, right? This is saying for the current day we can just eat whatever we want and it's not going to change. And but we have temp I equal to this, right? It does make sense. But hold a second. Equal temp I, and what the hell is this? What is J? J is this coming out. Huh? Group all jobs from J to I together, which means temp J minus job difficulty J plus. Okay, I know why we do this plus job difficulty I. What does this do? What is temp J? Temp J is all the way to J, right? With the number of subarray. And then we have the new one, right? So this is kind of the minimum. And because each time when we have this, we always consider job difficulty J to be the maximum. We consider job difficulty J to be the maximum of the current subarray. Therefore, as we go through the stack, right, once we incorporate the previous one, right, then to compute it, the current, that's why we say temp J, because temp J is the minimum like total with the last subarray ending at J, right, with the last subarray ending at J. And we want to know, excluding the last subarray, right, excluding the last subarray, what is the remaining, and a plus job. That is correct. Oh. So we do that to update temp I, okay? And eventually we'll hit a point where because we pop the small until we hit something big, okay? And if stack include the ith job with the stack. If stack, so the current one is smaller, and if it's smaller, we can be including the previous subarray because the previous subarray is still big. Because you want a fact, so we're including the previous one. What the hell? And then we do minimum of these. okay? And the stack will append I, because I now is smaller than the stack minus 1. So the next one comes in, and then we do the same thing, right? We do the same thing. But then this one doesn't make any sense, because temp I will be the minimum of this and the previous one. This is whatever including this. We always add this. But if the temp, the previous one is smaller, we basically use the previous one, right? We use the previous one. But in the future, how do we justify minus? If the table is smaller, then we have the possibility to group all the jobs from this to job I, because they all have the same max difficulty. Yes, this is correct. This might reduce the counting of multiple local high job difficulties. Yeah, I can see the benefit. I can see the benefit of this. Actually, I don't know. So we are popping the ones. Yeah, we're popping the one that's smaller, right? So we pop. So everything in between is smaller. So yeah, basically everything in between is smaller, and then we say if they're smaller, we can try to include them. Okay, it makes sense. Yeah, and in between, because the monotonic decreasing, right? Everything in between the two values in the stack is always smaller. So we just skip those, right? We skip those. Okay, until we hit something that's bigger. Right, until we hit something. So we have to go through everything, right? So until we hit something that's bigger. So in my idea, we'll keep going. And when we keep going, the current one will become this. This will be the max, right? Will become this. And we'll have to find the previous. Right, we'll have to find the previous. So yeah, this is where hold on. This line is was key, but I still don't. So there's something that's smaller, right? It's smaller than you, and we need to include. But how do we find? I'll probably go with dpj minus 1. I'll probably go with dpj minus 1 plus job difficulty I. I think that's how I would do it. dpj minus 1. Because it's the previous day, right? To j minus 1, and then j is including into the next one. That's how I do it. And then that will make sense. And then if stack, then yeah, if stack, which means you don't have to keep moving to the left because you already handled it. So just equal to this. I hope this is where I make the change. I still don't make the change here. I see the explanation here. This one, Uh-huh. Yes, or pop it from an update. Yeah, this is what I don't understand. Which I am going to just, out of curiosity, I'm going to go for Python on this. And instead of doing this, I'll do dp j minus 1 plus this. Let's see if it works. Yes, this makes more sense to me. This makes more sense to me. All right. I think it's perfect. It's perfect. We are going to I already have this one, right? 34. We already have this, and we're just going to go this and move it. In fact, I'm going to leave it here. Okay, I'm going to leave it here, and maybe we'll do it tomorrow. And after tomorrow, we'll move it back, and then we'll have to do it again. Lord, just keep. Now let's do this. You just keep accumulating all these problems. Anyway, all right, that will be it. That will be it for today. It's good experience. The O(n) squared d solution is not difficult to figure out, but the O(n) d one is pretty hard. All right, that will be it. I will see you guys tomorrow. Adios.